Hi all, my name is Song Ziwu. Today I'm going to present my final project for EEL6825. My topic is helpful memes classification with multimodal learning. Multimodal learning as an emerging deep learning technology combines natural language processing and computer vision. Basically, a multimodal model consists of image embedding and text embedding, as well as the fusion of those extracted representations. The concatenated embedding can then be used for downstream tasks. Memes combines image and customized text, which serve as a useful method for sharing ideas through the internet. The majority of the memes are friendly banter, though some are created with hateful emotion. It is necessary to detect and filter those hateful memes before people seeing it. The detector should be able to understand the text in the image and align the text with the corresponding regions of the image. However, extracting and understanding the underlying knowledge from convoluted visual and linguistic data is very difficult. Exploiting the power of neural networks, some researchers have tried to explore the method for detecting hate speech. An extensive use method is to first generate the word embeddings of the sentence. Then a binary classifier is developed for taking the embedding and outputting the results. However, the bias and unclear definition of hate speech bring great challenges for accurately extracting the information. Some researchers made an attempt towards multimodality. It is shown that the adding visual knowledge performs better on detecting the hateful speech. Although detection of hateful speech has made a great progress, currently the method is not able to be applied on the detection from memes due to the difference between the speech and image. Generally, the vision language tasks, especially the vision question answering, which have attracted a lot of attention recently, could be used to characterize the hateful memes detection. A common framework is merging the independent image embeddings and word embedding for prediction. The convolutional neural network and recurrent neural network are adopted as encoder for extracting visual and linguistic representation. The development of VQA benefits from computer vision and natural language processing with the emergence of ResNet and Transformer. The attention mechanism was introduced into the framework. The new challenge is how to merge multimodal features for memes, as the reasoning between visual and linguistic representation is the most important part than merging abstract features. The successful methods on traditional visual question answering could not be directly transplanted to memes, since the semantics of image and sentence meaning are not aligned and sometimes even irrelevant, as you can see in this figure, especially the last image. This project is inspired and incubated from a paper which participated in hateful memes challenge proposed by Facebook. The main objective is to determine if the sentiment of a meme in social media is helpful. It proposed architecture exploiting the power of decoding triple relation of image caption, OCR text, and visual features. In this project, the influence of model complexity, including ResNet 50, ResNet 101, and ResNet 152 are compiled, besides true effect of triple relation with them. Two datasets, hateful memes detection challenge dataset, aka HMDC, and Microsoft common objects in context dataset, aka as MS-COCO, were used in this project. HMDC is an open source dataset provided by Facebook containing 10,000 memes images with text file. This dataset is designed for binary classification. The whole dataset is split into training set, depth and test set with balanced classes. MS-COCO is an open source dataset provided by Microsoft containing 12 and 3,000 images with captions. This dataset is designed for image captioning. The whole dataset is split into training set, validation set, and test set. Back translation have been applied on text data to increase diversity as a data augmentation method. We use the back translator to add English to German to English and another one for English to Russia and then back to English. Besides, bin size of 2, 5, and 10 were used for generating different versions of a sentence. This figure shows a pipeline of training. Basically, the upper process is image captioning, which extracts the information of description. The lower one is the ensemble architecture, including OCR encoder, object detector, and a sentence decoder at first stage. And the three extracted components are fed into a triplet relation network to generate merged representation. Finally, a binary classifier with fully connected layer is used for handling the output of triplet relation network and making the prediction. A pre-trained ResNet is used as an image encoder for extracting the representation of the images. Then the image representation is mapped to sentence embedding via a sentence decoder. Image caption and OCR extracted text are two inputs of sentence. A tokenizer is exploited for breaking the sentence. The sentence embedding consists of 3 embeddings, including position, word, and segment. Then a token is added to the sentence embedding to form an embedding. A pre-trained faster RCNN is used for extracting visual representation of individual objects in the image, keeping a fixed number of region proposals. The purpose of triplet relation network is to construct a bridge between extracted vision representation, sentence embeddings, and OCR sentence. A pre-trained transformer-based model, BERT, fulfills this functionality of cross-attention. Array encoder consists of 3 matrices, queries, keys, and values. The outer product of Q and K is normalized by the dimension of the K. A softmax is used to calculate the probabilities. Then the inner product of a resulting matrix and V will be the output edge. A two-stream strategy is proposed as developing 2 independent paths for visual and text processing that interact through co-attentional encoder blocks. Multiple attention layers are stacked for constructing relations between modalities. The final output of last layer is taken as the combined representations. The combined representation is fed into a fully connected layer followed by a softmax layer to get a probability. A binary cross-entropy function is used as the loss function. For training the image encoder, the training batch size was set at 100. The initial learning rate is 1e minus 4 and gradually decaying to 4e minus 5. Adams was selected as optimizer. For training the object detector, the hidden size of the transformer was set to 768. Learning rate is 5e minus 5 for 10,000 echoes. Adams was selected as an optimizer. Performance matrix is the area under a curve of the receiver operating characteristic, known as EEL6825, which measures how well the means predictor discriminates between the classes as its decision threshold is varied. Here are some visualization results in this picture, which indicates the prediction and bounding boxes of objects. Apparently, the model is able to understand the underlying meanings of the memes, even if the image and the text is irrelevant, such as last two memes. The image captions provide a good guidance on generating joint representation. The model complexity plays an important role in training a model which is balanced between being robust to overfitting and maximizing the performance. The original paper adopted a pre-trained ResNet 101 as the image encoder for extracting the representation of the image. To investigate the influence of model complexity, experiments for ResNet 50, ResNet 101, ResNet 152 has been conducted. EEL6825 was selected as evaluation matrix. The results are listed in this table. The original ResNet 101 achieved best performance. ResNet 152 is expected to have highest EEL6825 since its capability of extracting more abstract features from the image. However, there's a significant drop in the performance. The reason may be the singularity of memes. As mentioned before, there is a huge gap between images and text in the case of memes, which are weakly aligned and even irrelevant. A better image encoder may not be the best fit for the reasoning of images and text. Some feature extracted by ResNet 152 may be useless for the reason. As for ResNet 50, its performance is slightly lower than ResNet 101. However, the time it required to completing the training is much shorter than ResNet 101. So I would suggest using ResNet 50 to train performance for more efficient resource utilization. The triplet relation network was a thorough investigation. The original paper doesn't discuss the weighting of the influence of two different textual embeddings. The experiments were conducted for object features plus OCR text plus image caption and object feature plus OCR text and object features plus image caption. The results shown in this table indicate that original setup with 3 embeddings obtained the highest score. The performance of object feature plus OCR text is lower than 3 embeddings, but is higher than object feature plus image caption, which suggests that the influence of OCR text is more important than image caption. Well, those two both help to improve the performance. To make a conclusion, in this project, a multi-modality method proposed by Zhou was used for hateful memes detection. This model constructs a triplet relation network combining OCR text, image captions, and images to enhance cross-modality relationship modeling. The performance is very promising. Further, the influence of model complexity was investigated. Experiments for ResNet 50, ResNet 101, and ResNet 152 have been conducted. Although ResNet 101 has highest AURC score, ResNet 50 is suggested since it's more friendly for computational efficiency. Finally, an experiment for studying the weighting of different components of a triplet relation network shows that image caption and OCR text both contribute to the improvement of performance, while the weighting of OCR text is more significant. So this is all for today's presentation. Thank you.